Hello and welcome again to my Physics Online video lecture series. In today's video, I'm going to be introducing a new concept, which is the concept of inductance. There are two basic types, mutual and self-inductance, and maybe briefly discuss some devices called inductors, which have this basic property. This is another basic circuit element that I am in some sense introducing today. Kind of akin to capacitors or resistors. Capacitors, of course, had capacitance, and resistors had resistance. Inductors have inductance. And so we're going to consider that in today's video. So let's dive into that. We can begin by recalling that Faraday's law predicts electromagnetic induction, and not only does it predict electromagnetic induction, but it kind of gives us how much EMF we expect to be induced as a result of a change in magnetic field flux. And so my induced EMF, which I may stylize with the subscript IND, is, as a time average, the basically rate change delta phi b over delta t, the rate change of the magnetic flux, and maybe times the number of loops through which that flux is being changed. So this is the basic Faraday's law, and it's what underpins the idea of inductors. So let's consider now a pair of solenoids. And so another thing that we need to recall here is current produces a magnetic field. And so, for example, this is via Faraday's law, via Ampere's law. So, for example, you might have a pair or a single solenoid. So, example, ideal solenoid, the magnetic field is given by B is equal to mu naught times little n times I, or in other words, mu naught times big N divided by length, axial length, times current. So here we have magnetic field related to current, to number of turns in our solenoid, and to the axial length of the solenoid. Axial length, of course, being if I have a solenoid and it's got windings like this, then the axial length would be this right here. How long is the, let's say, tube that you've wound the wire around? And in, I have here 1, 2, 3, 4, 5, 6, 7 windings in this thing's case. All right, so now let's consider two solenoids. All right, so let's say that I have a solenoid here like this, and it has some number of windings, it has some number of whatever. I'm not specifically trying to draw a particular number of windings, I'm just trying to draw here a solenoid. And now let's say that I have a second solenoid which is embedded in the first, like so. Hopefully this purple is not too hard to see. Here's a color with a little bit better contrast with the black. So I have a second solenoid which is embedded inside of the first. So we can label this one number 2, we can label this one number 1. If I run current through solenoid number 1, then this means that I have a magnetic field inside of solenoid number 1. So let's call this the B field right here, which I'll just draw in blue. The B field basically should look like this, and then outside, of course, it kind of curves away like this. But inside, I just have a B field. We'll call this one B1 because it's the B field produced by number 1, and that has a magnitude B1 of current 1 times mu naught times the essentially like density of the windings. Now let's say that I just want to look at coil number 2. So coil number 2, as long as this stays as is, there's no change to the current or anything, coil number 2 doesn't really experience any kind of flux changes. But if I start changing the current, maybe I have an AC signal, maybe I just happen to have a current that is being shut off, and so it's like dying down slowly. Like maybe I am slowly dialing it down to 0, something like that, or slowly raising it up to the final value, whichever. Well, that would imply that the magnetic field is changing, and that in turn implies that there's going to be a change in the flux seen by coil number 2. So here's my cross-section area for coil 2. Phi sub B in coil number 2 should look like B1 dot A, where this one right here is my cross-section A, and then we could call that A2, if you will. So this is the flux through coil 2, and that has to be times the number of loops in number 2. This one right here, this one, if we wanted to be really specific, would look like mu naught times I1 times number of loops in coil 1 divided by the axial length of coil 1. Okay, so coil 2 now sees this flux. And if I start changing the magnetic field, then I'm going to get a change in the flux here. If I start changing the current, that's going to change the magnetic field. That's going to give me a change in flux here. Now you can imagine that this calculation, even on its surface, looks fairly complex. And I've picked here one of the simpler geometries. We already know how to find the magnetic field inside of a solenoid, an ideal solenoid. You can imagine that it's more complicated if I have like a square piece of wire and another square piece of wire nearby, like a square-shaped loop and a triangular-shaped loop or something like that, where it's not an ideal solenoid. Or even if I like move the two apart so that I've got a solenoid in one location, I've got another solenoid nearby but not just inside of the first one. It gets pretty complicated because we have to basically calculate this thing in order to get the delta phi on 2 by delta t in order to get the epsilon induced in coil 2. And so that's a bunch of different calculations. So there's some good news here. And the good news is this. We can introduce this concept of inductance. And this concept of inductance lets us replace rate change of flux with a simple rate change of current, which is nice because you can just measure that by having an ammeter and a stopwatch, or something more sophisticated like a current probe and a computer. Now in the setup that I've drawn, it's a rate change of current in number 1, which is producing a EMF, an EMF in number 2, inducing one. So as it turns out, if I were to change the current in number 2 instead, then I would induce an EMF in number 1. So each of these two coils is able to induce some EMF in the other coil. So this process is called mutual induction, And so we have, in this case, mutual inductance. And as it turns out, the mutual inductance is specified always for a pair of objects. So the mutual inductance, we usually use an M. There's also another concept called self-inductance, which basically goes like this. Suppose instead of having two coils, suppose I looked only at one coil. So I remove coil number 2 and just look at coil number 1. And I begin to run some current through coil number 1. Well, that means that I begin to produce a magnetic field in coil number 1, and that means that I begin to have a flux that I didn't have before. And if I start increasing the current, then I start increasing the field and hence the flux. And therefore, I will induce some what's called back EMF in coil number 1, and that's without coil 2 being present at all. All right, so to summarize, mutual inductance, coil 1 induces EMF in coil 2. If you change coil 1's current, coil 2 induces EMF in coil 1 if you change coil 2's current. And so the property mutual inductance, we use an M. Self-inductance, coil 1 taken by itself without coil 2 being present induces what's called a back EMF when the current changes. It's called back EMF because it will tend to resist the change in current in coil 1. Okay, so how do we define these two terms, self and mutual inductance? Well, for mutual inductance, we basically can say that the EMF induced in coil 1 is equal to the mutual inductance of 1 and 2. And I guess we could label this 1, 2 if you'd like. Sometimes we just label it M, but it's negative of the mutual inductance in 1 and 2 times rate change of the current in coil 2. And the EMF induced in coil 2 is equal to negative of that same mutual inductance, M12, times the rate change of the current in coil 1. It's not a very good number 1, though. So basically like this. So these are both true. For self-inductance, which again we use an L, the equation looks more like this. The induced EMF, let's say in coil 1, is equal to negative L times delta of the current in coil number 1 divided by delta time, in other words, rate change of current. Now, the nice thing about inductance here is that instead of having to calculate flux in every conceivable situation for every conceivable current change, what you do is you calculate what the value of the inductance is, either the mutual or the self-inductance. And then as long as you don't change anything with the setup or geometry of the system itself, you can use any kind of applied current and get the EMF from it. In other words, you do one complex calculation one time for your system, and then it's easy calculations from there on. In the case of the other way around, just calculating from Faraday's law, you may have a complicated calculation each time that you change how you alter the current. So this is, it's like more work up front, and then it's easy from there. A last little note about mutual versus self-inductance is this. With mutual inductance, to calculate it, you need to know quite a few parameters. You have to know about coil number 1, and you have to know about coil number 2, both taken on their own. Meaning, like, how many windings does each have, how long along the axis, how much rate change of current are you going to apply to each one, but especially like how many windings, how long, and then how big is the winding. So how much area is encompassed in each winding. And that, of course, goes back to the fact that you are ultimately basically shortcutting the Faraday's law, where you have an area involved in the flux, and you also have a number of windings in both coils. So you have to know all those information. But you also have to know where the two coils are relative to each other. So, for example, if I have a setup like this, where coil 1 is here and coil number 2 is here, I'm going to get a different mutual inductance than, let's say, if I have coil number 1 here oriented like this and coil number 2 here oriented like this. These will have different values of mutual inductance. Basically, the placement of the two coils, how far apart are they and how are they oriented relative to each other, is also sort of a factor in all this. Therefore, you kind of have to calculate the mutual inductance in a case-by-case basis. There's no simple formula outside the definition that says, oh, the mutual inductance for two solenoids will be this. Because if they're very far apart, it's going to be different than if they're very close together or embedded in each other. If they're oriented crosswise to each other, as in this picture on the right, then it will be different than if they're oriented coaxially, as on the picture on the left. Or side by side will be different as well, etc. With self-inductance, you don't have necessarily this problem. So self-inductance, which is what we usually mean if we just say the word inductance, we're usually referring to self-inductance. And usually we include the modifier mutual if we need to specify mutual. This is only one coil, and so it's just the properties of that coil. Thus, we can get a particular geometric properties, number of coils, length, area of a coil, or area inscribed by a coil, cross-section area, whatever you want to say, that one turn surrounds. And those parameters will let us get what is the self-inductance going to be for a solenoid, or for a toroid, or etc. Okay, so self-inductance, you have a calculation you got to do, but you do it once and you're done, and you now just kind of modify things like how many windings, or how long is the thing, or how big is a winding cross-section area-wise. So it's easier in that sense. So in a future video, like I said, I'll discuss self-inductance a little bit more in terms of some specific geometries, similarly to how I've done capacitance for capacitors depending upon plate area and separation distance for a parallel plate capacitor, similar to how I've done resistance based on resistivity and wire cross-section area and wire length for resistors. Okay, but that is for a future video. I think that this video is long enough for an introduction to this idea of inductance. So that's all that I'm going to do today. Hopefully you've learned something, and hopefully also you're interested in learning a little more. And as always, thanks for watching.